to get this basic K matrix, which we called it as a simple pinhole model. Sometimes the F, which is the focal length, this is the focal length in X, this is the focal length in Y. And then at most, we have radial lens distortion that we need to correct as well, which is this. This is what we call a barrel distortion, which needs to be corrected. Otherwise, none of those formulations would work, right? A point on this from the camera going towards the reality is not going to be in the same line, I guarantee you. It's going to curve. We want to make sure that that doesn't happen, okay? So we want to decompose or what we call undistort this image back to how it was in reality. And sometimes you might have something else called pincushion distortion. Regardless of what it is, you have particular terms for radial lens distortion. It's mathematical there. I'm not going to go into the details about the mathematics, but there are various topics that you can actually go through, particularly in photogrammetry and calibration. What we want is to be able to find the terms for radial lens distortion in order to undistort the image from either this barrel or this pincushion, and to extract our remaining camera parameters, which is F and PX and PY. So going back to the calibration process, as I mentioned, these 3 points, the perspective center, the corresponding image point pixels, and the object space coordinates have to be in the same line, right? If they're not in the same line, that means there's a problem. So what this means is that we have to create some sort of system in order to be able to find what a particular point is in the image and what that representation is in the object space. We can either use these checkerboards, and these checkerboards are very famous and popular. For instance, MATLAB's calibration actually uses these checkerboards. Basically find the representative feature of this checkerboard into another image that you've taken, and then from that you enforce it through this collinearity, and then you get the calibration parameters that you want and you require. Or the way that I've done it, and previously I've worked on this quite a bit, is to perform calibration in a calibration room through black and white circular target. So one of the problems with the checkerboards is not necessarily that, you know, it's bad. If you have it in very large scale, you would be able to get it, and you can get basically images from it. The major problem that, let's say, this implementation that is on MATLAB's website, and I really wanted to bring this forward, is that we have all of these space, 2/3 of this image, that has not even had any representation. If you don't have any representation, how are you expecting to be able to properly extract the information regarding the radial lens distortion and other types of distortions? You can't do that. And the other thing is, what they've done is they've basically had it in the same location, and then they're moving this target field. For me, what I basically generated, particularly as a methodology for smartphones, was that I use these targets that you can attach anywhere that you want, and then you collect videos, or you collect a bunch of pictures in let's say burst mode, and then you stitch it together, do basically all of these computer vision work to extract what the scene is. And then I also have my methodologies to extract the ellipses, which basically these circular targets are represented by ellipses as images. And from those ellipses, you can get the centers of them, perform a correction for the eccentricity. And then from that, we basically have our ideal set of points where we can now use that in order to perform what we call a bundle adjustment, in order to adjust the overall characteristics, get the camera matrices, camera information, and the radial lens distortion problems. But one of the other benefits is basically it has to be well distributed, meaning this target field should be everywhere. And if it's everywhere in the image, then it has good amounts of representation, because now you can get all of the other information that you want from it much more accurately, with much more certainty. rather than it being skewed towards a particular area in the image, which, for instance, in these cases, in MATLAB's recommendation, you see it. So how do you collect the data in order for it to give you good, proper information? I didn't go through the mathematics behind how you even write the collinearity equation, all of these things, because I feel it's not necessarily relevant. However, I believe how you collect the data is relevant because it's very pragmatic and practical for us. One is that because of these massive matrices that you're going to be creating with all of these points, for solving, let's say, the collinearity equation, you need to collect both in portrait and in landscape. This would give you a minimization. It would minimize the chances of correlation between certain parameters of your interior orientation, which is your calibration parameters. Another way that you have to minimize this is by creating depth, meaning that you have to collect data from two different basically distances from your target field. If you don't do that, then your information about your basically direction towards the depth might also be skewed. And also you might have some problems with correlation between particular variables in your calibration, which you don't want. So if you want to calibrate something, you have to do it in both portrait, landscape, and you also have to create depth. So go forward, go backward in both directions as well. The other aspect is convergence angle. So if we do it like this, you see the noise that you have created in your object space point clouds is very, very bad. You see it here as well. But if we do it, let's say, convergent, this is where you have your images looking towards the target rather than it's basically looking outside of it and just corners of it looking at it. You're going to get a much better accuracy in your images, and it's very important for your calibration as well. And the accuracy of the reconstructed scene is quite higher as well.